we have a model of a robot. We know how the robot can get position information. In this case, we use the wheel encoders, but there are other ways. We talked about compasses and accelerometers. But the robot also needs to know what the world around it looks like. And for that, you need sensors. And we are not going to be spending too much time modeling different kinds of sensors and see what is the difference between an infrared and an ultrasonic range sensor. Instead, we're going to come up with an abstraction that captures what a lot of different sensing modalities can do. And it's going to be based on what's called the range sensor skirt. This is the standard sensor suite on a lot of robots. And it's basically a collection of sensors that are the collection that is gathered around the robot that measures distances in different directions. So infrared skirts, ultrasound, LiDAR, which are laser scanners, these are all examples of these range sensors. They're going to show up a lot. Now, there are other standard external sensors, of course, like vision or tactile sensors where you have bumpers or other ways of physically interacting with the world, or GPS, or I'm putting them within quotation because there are other ways of faking GPS. For instance, in my lab, I'm using a motion captioning system to pretend that I have GPS. But what we're going to do mainly is assume that we have this kind of setup with a skirt around the robot that can measure distances to things in the environment. And in fact, here's the Capera. It's a simulation of the Capera. And the Capera in this case has a number of infrared sensors. And well, you see the cones. You have blue and red cones, and then you have red rectangles. The red rectangles are obstacles. And what we're going to be able to do is measure the direction and distance to obstacles. So this is what type of information we're going to get out of these range sensor skirts. Over here on the right, you see two pictures of the sensing modalities that we had on the self-driving car that was developed at Georgia Tech. And we have laser scanners and radars and vision. But the point is that the skirt doesn't always have to be uniform or even homogeneous across the sensors. Here we have a skirt that is heterogeneous across different sensing modalities, but roughly you have the same kind of abstraction for a car like this, as well as for a Capera little mobile differential drive robot. Okay, so that's fine, but we don't actually want to worry about particular sensors. We need to come up with an abstraction of this sensor skirt that makes sense and that we can reason about when we design our controllers. So what we're going to do is we're going to do or perform what's called the disk abstraction. So here's the robot sitting here in the middle. Around it are sensors. And in fact, if you look at this picture here, here are little infrared sensors. And in fact, here are ultrasonic sensors. So you see that scattered around this robot is a skirt of range sensors. They typically have an effective range, and we're going to abstract that and say there is a disk around the robot of a certain radius where the robot can see what's going on. Right? So this is this pinkish disk around the robot, and it can detect obstacles that are around it. So the two red symbols there are the obstacles. And in fact, what we can do is we can figure out how far away are the two obstacles. So D1 is the distance to obstacle 1, which is this guy, and this is obstacle 2. Well, okay, so I'm drawing with red, so it didn't show up. And phi 1 is the angle to that obstacle. Similarly, D2 is the distance to obstacle 2. Phi 2 is the angle to obstacle 2. One thing to keep in mind, though, is that the robot has its own coordinate system in the sense that if this is the x-axis of the robot right now, then phi 1 is measured relative to the robot's x-axis, so the robot's heading. Right? So we need to take that into account if we want to know globally where the obstacles are. So let's do that. If we have that, and if we know our own pose, so we know x, y, and phi, then since the measured headings to the obstacles, so this is phi 1 which we're measuring, and we're measuring this relative to our own orientation. Let's say that our orientation is this, right? So here is phi, and here is phi 2, say. Then, of course, the actual direction to obstacle 2 is going to be phi 2 plus phi. So what we can do is we can take this into account and compute the global positions of these obstacles if we know where the robot is. So for instance, the global position of obstacle 1, x1 and y1, well, it's the position of the robot plus the distance to that obstacle times cosine and sine of this phi1 plus phi term. So we actually know globally where the obstacles are if we know where the robot actually is. So this is an assumption we're going to make. We're going to assume that we know x, y, and phi, and as a corollary to that, we're going to assume that we know the position of obstacles around us in the environment. So that's the abstraction that we're going to be designing our controllers around. And I just want to show you an amusing example of this. This is known as the rendezvous problem in multi-agent robotics, where you have lots of robots that are supposed to meet at a common location, but they're not allowed to talk. They're not allowed to agree on where this should be by chatting. Instead, they have to move in such a way that they end up meeting in the same location. And one way of doing this is to assume that you have a range sensor disk around you. And then when you see other robots in that disk, instead of thinking of them as obstacles, we think of them as buddies. So what we're going to do, each robot is going to aim towards the center of gravity of all its neighbors, so everyone that is in that disk. And because of the disk assumption, or the disk abstraction that we just talked about, we can actually compute where the center of gravity is of our neighbors. So here's an example of what this looks like. Every robot is shrinking down all the robots shrink down to meet at the same point without any communication, simply by taking the disk around them, looking where are my neighbors in that disk, and now we know how to compute that, and then computing the center of gravity of my neighbors and aiming towards said center of gravity. Okay, now we have a robot model. We have a model for figuring out how to know where the robot is. We have a model for how do we know where obstacles and things in the environment are. Now, we can use these things, of course, to actually start designing controllers. So that's what we're going to have to do next. I do want to point out, though, that the model, the wheel encoder, and the disk abstraction, these are but an example of what you can do and how you should make these kinds of abstractions. But for different kinds of robots, different types of models and abstractions may be appropriate.